Welcome to 6.03. We're going to work on finding trigonometric values for radian measures between 0 and 2 pi. And so that might sound a little weird right now. Don't worry, it will make perfect sense in just a bit. And radian measures between 0 and 2 pi should already be starting to make a good amount of sense. If you feel like you need a little bit of a refresher, go back and review 6.02, look at some notes so that you feel confident going in here. I want you to review the problems that you worked on in class, in the last class, so that you feel confident in how angles measured in radians kind of work. So go through and make sure that you are finishing up. If you didn't get done with 3 and 4, give those a try. And then I also added one more new angle to convert into degrees, which would be an angle measure of 1 radian, which I think could be helpful in converting further and just kind of understanding more. And then we'll go over these quickly and then move on to some more important concepts. So on the left side here, I've just completed and went through these already, and so they should make sense. And then here for 1 radian, in order to find the angle in degrees, that is 1 radian, remember that's 1 radius length, what we would do is we'd start with the fact that pi radians is 180 degrees and divide by pi on both sides, and 180 divided by pi is 52.3. And this should make sense because when we looked at a 60-degree angle, we saw that it was approximately 1 radian. Pi over 3 is a little more than 1, and so 60 degrees should be a little more than 1 radian. And it certainly is 52.3 degrees. So now moving on to number 3, and here this is not a unit circle, and so we want to go back to just kind of the very basics of a radian, and a radian being the number of radius lengths in the arc that subtends the angle, or that covers the angle. And so here this angle has an arc of 20 units and a radius of 8, and so the number of radius lengths in this arc, 20 divided by 8, is 2.5, so this would be 2.5 radians. And so I can use the fact that 1 radian is 52.3 degrees, and so I have 1 radian is 52.3 degrees, and I want to know what 2.5 radians are, so I multiply by 2.5 on both sides, and this will tell me that 2.5 radians is approximately 143.3 degrees. And this should make sense because if we look here, this is almost a full turn, right? A full turn would be, a half turn. Half turn would be pi radians, right? 180 degrees. And pi is more than 2.5, and so 2.5 radians certainly should be a little less than 180. Here, for number 4, it's best to actually draw a clock and think about, going from 12, 1, 2, and you work all the way back around. Here's 6 and here's 9. And we want to know if the minute hand of a clock rotates through 10 minutes. So you can choose to start your 10 minutes wherever. Let's just pretend it starts at 12 and it rotates 10 minutes, meaning it goes to 2. Okay? And the question is, what is this angle in radians? How far did it turn? And so what we want to do is we want to think about, okay, what's the, angle measure that it turns here? What's this arc length? And we know that a full turn is 2 pi, right? So if it turned all the way around, that would be 2 pi radians. And how much of the full turn did this minute hand make? Well, 2 out of 12, right? So that would be 1/6 of the way. Let me just go over this once more. So there are 12 numbers on a clock, right? So it rotated to 1 and then to 2 out of the 12, right? So it's 2 out of 12, and so what I'm doing is I'm taking 2 pi radians and I'm just taking 2/12 of it, or 1/6 of it, so multiplying by 1/6, and that will give me 2 pi over 6, or pi over 3 radians. Okay. Now if I want to compute that in degrees, I can use one of the facts that I already found, which is that pi over 3 radians is 60 degrees. So this would be 60 degrees. And that should make sense because if you turn 10 minutes on a clock, you've made 1/6 of the turn around the clock, and 1/6 of 360 is 60. All right, now we're going to move on to some new material, so get ready. I want to keep us on track for our goal that we talked about at the very beginning of the unit. And our goal was to find a function that could tell us the x and y values of these points that move around a circle. Okay? Because we realize that points that move around a circle are going to repeat. Right? So the x value is going to repeat, and the y value is going to repeat, and that will allow us to have a function which is going to repeat itself. So I think about a Ferris wheel. I've gone around once, gone around twice, and it follows the same path. So this is what is called a periodic function, right? It has a period in the sense that it has one period and then another period, and we'll just continue on. And so our goal was to be able to write a function to find the x and y coordinate of points that follow around a circle. And in order to do that, we had to come up with a way for actually moving around a circle and defining where on the circle we were. And that's where radians came in. Right? We talked about, okay, well, if you're, pi radians, that means you're halfway around the circle. If you're pi over 3 radians, you're, at a 60-degree angle, you've moved pi over 3 around your unit circle. And this has allowed us now to finally get to the point where we can start thinking about these specific points, because we have a way of talking about where those points are using radians. So that's what we're going to be working on today, and it's going to require you to dust off some information that you learned a little bit ago, which will be some right triangle trigonometry. We have a unit circle, and we are very close to being able to say how we can find the x and y coordinates of any point along the unit circle. So, for example, how do I define where the point is? Well, I can say the number of radians that I have to rotate to get to that point. So, for example, starting here, if I rotate pi radians, that will be 180 degrees. That point will be right here. If I rotate pi over 3 radians, 60-degree angle, I'll be right there. If I rotate 5 pi over 6 radians, I'll be about here. And I can go all the way around the circle and define the points as such. So let's go ahead and do that. So the way that we're going to work is we're always going to start from the positive x-axis of our unit circle, and a positive angle is going to rotate counterclockwise. Okay? So that's an important thing to remember. If you have a positive angle, that means you're rotating counterclockwise, and if you have a negative angle, then that means you're going to be rotating clockwise. Okay, so that's a couple of important things to note. Okay, and we're going to define the point on the unit circle. Let me just give it some coordinate points: x, comma y, and this is just a generic point. Remember, this way we can represent any point on the unit circle as the point once I've rotated a certain angle. So this is what's called the terminal side of an angle. We start at the positive x-axis and rotate counterclockwise, and when we stop, this is what's called the terminal side of the angle, and the point xy will be defined as the point on the unit circle once I've rotated a certain number of radians. And we're just going to call whatever angle this is, since we're just talking about a general case, we're going to use the variable theta to represent the number of radians that we've rotated. Okay, so this is the Greek letter theta. I'll draw it a little bigger here, and that is the variable that we often will use to refer to an angle that we don't know the exact value of yet. And so the question is, how can I find the x and y value of this coordinate point? All right, so I want you to, on your own, go ahead and try and come up with a way to do this. Now, I'm not expecting you to get it right, but you want to have thought about it so that you are more prepared to see the actual correct answer. So try some things out. My one hint would be to try drawing some shapes that you are familiar working with, and then go ahead and press play, and we'll talk about the actual ways to compute x and y. All right, so the first thing that will help us get on the right track is noticing the length of this line segment here. And since the circle has a radius of 1, you know that the length of this line segment is also 1. Now, we are trying to compute the value of the x-coordinate and the y-coordinate. And notice that the x-coordinate just refers to the x distance, right? So if I drop a line down and think about the x distance, that's just the distance in the x direction along the x-axis. So I can actually mark that. I'm going to color code it here so that we can see it better. That is the value of x, right? And y, same thing. Y is the vertical distance, so the distance in the y direction. And so I can drop a perpendicular down that will give me the y value. And these will meet at a right angle, right? And this refers to the y value. And so now that I have a right triangle here, notice this right triangle where one of the sides is the x value and the other side is the y value, it turns out that I'm just going to use some very basic principles of trigonometry that you've already learned to compute the x and the y value here. Okay? So I want you to pause the video now and dig back into the recesses of your mind to geometry and think back to the things you learned about right triangle trigonometry and see if you can come up with some relationships that will allow you to find the x and the y value in terms of whatever this angle is here. Remember, it's important that we're using this angle to determine what x and y are. So try it out, and then we'll discuss in a few seconds. All right, so hopefully you thought back to sine, cosine, and tangent, and how the sine of an angle is the opposite side over the hypotenuse. The cosine of an angle is the adjacent side over the hypotenuse. And then it will allow you to think about, okay, well, the sine of this angle is going to be very helpful, and so is the cosine of this angle. And let's just see how that works. So let's think first about the sine. Okay? So the sine of this angle theta, that's how it's drawn there, the sine of this angle is the opposite, which is the y value, over the hypotenuse, which is 1. Well, what is anything divided by 1? It's just going to be that something. And so the sine of theta is the value of y. Okay? Remember, the sine is the opposite over the hypotenuse, and so the sine of theta is y. Let's check out the cosine. Cosine of theta. And why don't you pause the video and try this one yourself. So the cosine is the adjacent over the hypotenuse, the adjacent side of this triangle, this angle theta, the adjacent side is the x side, and the hypotenuse is still 1. And so the cosine is x over 1. Anything divided by 1 is itself, and so the cosine of the angle theta is the x value. And so here you have it. For any angle that I've rotated, any angle theta, the coordinates x and y are given by the sine and the cosine. The cosine of this angle will give you the x value, and the sine of this angle will give you the y value. It's pretty simple. So for any angle theta, this point x comma y, the x value is going to be the cosine of that angle theta, and the y value is the sine of that angle theta. Okay? So now we have a way of computing the x and y values of any point along the unit circle, simply by finding the cosine and the sine of these angles, of this angle theta. All right, so that's been a lot, and what I'm going to do now is I'm going to define very clearly the sine and cosine and what they mean for us in terms of the unit circle. And this is where the idea of sine and cosine really come into effect. And so the sine of an angle theta is actually defined as the y value of the point along the unit circle. And the cosine of an angle theta is exactly the x value of the point after you've rotated that angle theta around your unit circle. So I'm going to go ahead and write that out for us so that we have it, and then give us one last thing to think about in preparation for actually finding some values of x and y for some particular angles around our unit circle. All right, so here they are written out. The cosine of an angle theta is defined as the x-coordinate of the point where the terminal side of the angle theta intersects the unit circle. So terminal side, the terminal side, as we discussed before, is this side where the angle finishes. So I start always along the positive x-axis, and the terminal side of the angle is where the angle finishes. So that's the terminal side of the angle theta. Here's this angle theta, right? And where it intersects the unit circle is this point, of course, and the x-coordinate is the cosine of that angle. The sine of theta is the y-coordinate of the point where the terminal side of my angle intersects the unit circle. And so sine and cosine are going to be values that are going to repeat themselves. The cosine of this angle, the x value, is going to repeat itself as we go around the unit circle. And the sine is going to also repeat itself as we go around the unit circle, which is going to give us that periodic function. So think about what is it that we're going to need to compute the x and the y value. In other words, to compute cosine and sine. Well, we're going to need to know the angle theta, right? When we know that angle, we can compute the cosine and the sine of that angle, and that will tell us the x and the y value of this coordinate point. And in order to do this by hand, we're going to have to look at some right triangles that we actually are familiar with. And so we're going to do that in just a second. The last thing that we're going to talk about briefly is what is tangent. So tangent of theta is the opposite over the adjacent. And so the opposite side of theta is y, and the adjacent side of theta is x. So the tangent is just y over x. In other words, the rise over the run. And so tangent is often thought of as the slope of this terminal side. The slope of this terminal side. And is equivalent to y over x. And if you think about it, right, the y value is just the sine, and the x value is the cosine. So you can compute the tangent of an angle theta just knowing sine and cosine, right, and taking the sine of theta and dividing it by the cosine of theta. Okay? All right. So to get us prepared for what we're going to do tomorrow, which is actually computing the x and y coordinate points, or the cosine and sine, and then of course the tangent of some points along my unit circle, I'm going to have you kind of create your own unit circle where you have some special angles already written out on your unit circle, so that you have an idea of kind of what we're going to be able to look at on our own. All right, so on this unit circle, we're going to mark some angles here, 30, 45, 60, and 90, and mark them with their radian measure. So let's do 60 degrees together. Remember, this is the initial side of our angle, and we rotate counterclockwise around the unit circle. And so if I'm going to rotate 60 degrees, that's, 90, 60 would be about here. Okay, like that. And I always denote an angle by writing that arrow where it starts and then points towards where the terminal side finishes. Here is the point at which it intersects the unit circle, and I'm going to label this angle, right? This is the angle that's rotated pi over 3 radians, right? Because this is the length of that arc, and so I'm going to label it as pi over 3. Okay? And so on your paper, make your sketch much bigger so that you can fit, 45 and 30, and also label those appropriately with the correct radian measure. Make sure that you post a comment with a question that you have, so that you've already have something that we can get into and discuss at the beginning of class tomorrow and move on to expanding our knowledge of the unit circle.